Alright, before we proceed with this section, loci in an Argand diagram, we shall do a little bit of recap. Right. Now, given a complex number z, say z is equals to x plus yi form, right. We know that the modulus of z is given by the square root of x squared plus y squared. Now, if you were to actually plot the representation of the complex number z in an Argand diagram, it can be represented by this point P. So if let's say this is x, this is y, okay, the point P, as you see here, is the representation of the complex number z. Now you will notice that the distance from the origin to P, alright, that is OP, is actually the modulus of z, alright, and that is we already said it is equals to x squared plus y squared. If you were to look closely at the modulus of z, it can be written as z minus 0, yeah, and this is the length OP. Now, if you look at the modulus of z minus 0, it is as if it is representing the distance between the point P and the origin, because 0 can be written as 0 plus 0i. Alright, so the modulus of z given by x, the square root of x squared plus y squared, is actually the distance between the complex number z, right, represented by the point P, to the origin. The complex number z is represented by the point P, and the origin is usually represented at the point O. So from here it is quite obvious, from the modulus of z, which can be written as modulus of z minus 0, is actually distance, alright, from the origin to the point P. Now let's take a look at how we can extend the same idea with our first example of a locus, that is a circle. Say we take this equation, z minus a, alright, is equals to a fixed number k, bearing in mind that z refers to a variable complex number, in this case represented by the point P on the Argand diagram, and a is a fixed complex number represented by the point A on the Argand diagram. As we have seen just now, when we put a modulus of z minus a, it is the distance between the point P, representing the complex number z, and the point A, representing the complex number a. So what does this all mean? Let's mark out the point A first. Right, so let's say if I were to mark the point A here, alright, now I want to be able to find the point P such that the point P, the distance from the point P and the point A, is always k, according to this equation. So let's say I mark the point P here. Alright, so I must make sure that this distance is k. But then again, is this the only point, the possible point P, such that the distance is k away from A? No, right? So you realize that you can also mark another point P over here, alright, such that the distance again is k away from the point P. So essentially you realize that there are many points, there are many such points, and it actually forms a circle. And thus, having an equation of this form, right, it is actually a representation of the locus of the complex number in the form of a circle. Alright, I've just shown you clearly how the equation of this form z minus a equals to k, where k is a real positive constant, alright, defines the locus of P, which is a circle with the center at A and with a radius k. Right, so we need to remember that z minus a, the modulus of z minus a, actually denotes the distance from P to A, as I've already explained. Now, how do you check whether the locus that we have just defined is indeed a circle? Okay, one way is to check whether the Cartesian equation, alright, is indeed the equation of a circle, and this can be shown in the process that you see here. Now, your fixed complex number A, right, can be represented by a complex number P plus IQ, and your variable complex number Z can be represented by x plus yi. Putting that into the equation, you will realize, right, that you can actually arrive to this equation, which is indeed the equation of the circle with center PQ and radius k.